So, without further ado, let's go to our second lecture, or Water Balance of the Mining Waste Areas in Finland by Kirsi Haanpää from AFRI. Thank you.
Yes, thank you. Good day, everyone. So yes, now half an hour or maybe a bit less, like on topic water balance of the mining waste areas in Finland. First, just shortly about me. So now giving the speech is Kirsi Haanpää. I'm a leading consultant from AFRI. I don't have any company presentation included, but AFRI is a engineering and consultancy company, Swedish owned currently, formed by the union of Swedish ÅF and Finnish Pöyry some 5 years ago. We are 19,000 employees on the company. I'm located in Oulu in northern Finland. I'm Master of Science from Environmental Engineering from my educational background. Graduated from the Oulu University 2007, and I've worked with AFRI as a consultant since 2008. So kind of the reason why I'm giving this topic is that I've led projects. I worked in projects related to mine site water management, mostly to those technical solutions, how to manage actually the water on mine sites. Water balance modeling has been one of my favorite topics now for years. But I've also involved quite a bit to environmental and water permitting of Finnish mine sites. And I quite often find myself working on the interface between the technical and environmental teams. So that's kind of the background that I come from, so it's from experience. I only have 3 topics, my favorite topics that I want to talk today. It might be that we will not get to the third one actually too much. But it's hydrology in Finland and Nordics. This is the basics. How is it now and how is it in the future? How much we do get water and from where it comes from. Then it's mining waste areas and water. How water flows and cycles in rock and sludge. I don't have a lagoon bonds here on the presentation. I focus on waste rock, on rock stacks, and then on sludge bonds. And then if we have time, so just shortly about, this is my really favorite topic, but water balance is, so what is it when we do modeling of this net positive stuff? But with these topics, we go forward. Hydrology, this is kind of the, when we talk about Finland and mining, so it's to understand that where are we, where have we, on which kind of climatic and hydrological conditions we are located and how it will be in the future. We know the climate has changed, it will change, it will continue to change, but what does that impact for us? But there is a good track record of environmental and climatic kind of measurements in Finland, but average mean surface air temperature here is 2.5 degrees, but we are quite long country, like from south to north. In Lapland, we are still a bit below 0 on the average temperature, but in southern Finland, almost 5 degrees already. So there is a quite difference between the areas. Mining industry in Finland is mostly up north, also on southern areas, but kind of a majority of the mines are located a little bit like in the northern parts of the country. But yes, temperature is one thing, but then how it varies like during the year. So we have the winter still. There is freezing conditions, which means that there is also snow, and then there is a frost heave. And in summertime, obviously temperatures rise, but also in summertime the precipitation is higher. This is the curves that are presented here are just like for the whole Finland, really generic curves. But precipitation in southern and central Finland, that's usually between 600 750 millimeters. In northern Finland, from 450 to 650 approximately. Evapotranspiration is something like from 200 to 300 millimeters. So kind of a thumb rule is that the runoff is from, well, let's say from 300 to 400 millimeters annually. When do we get the runoff? In northern Finland still, in Lapland especially, so we still have the spring melt season almost yearly. So it's somewhere around May, even June. But when we come to southern Finland, so that's what we see, is that we don't have maybe that kind of we don't have one spring melt season anymore, so kind of the snow melts like during the winter, so we do have kind of runoff also more during the winter, like a little bit like more constantly and more unpredictably than it has been in the past. But this kind of thumb rules, really short look, just this is now temperatures, but because I will on the next slide go to the future, that what's the climate like in the future. But the upper graph is about the average temperature in whole Finland. The lower is it from the Lapland. But since like 1990s, that's when we actually, when looking at the long history, so that's when the really the change started to be seen, like concerning the temperature, but also the precipitation. And in the future, so IPCC sixth assessment report has presented these shared socioeconomic pathway climate scenarios. So when we look at the future, so projected average mean surface air temperature, so yes, that will continue to increase till 2040s, until 2040s approximately. The scenarios kind of response kind of quite the same way, no matter which shared socioeconomic pathway or climate scenario is chosen, but then they start like diverging. So temperatures do increase, but also precipitation increases. And this is also kind of the same kind of pattern is seen here. So for me, kind of, I do a lot of kind of practical engineering at the work. There is a lot of data to analyze when we talk about climate and climate change. But kind of, we continue having this quite the same kind of climate here also in the future. Predictability of the climate, when do certain occasions happen? So that's not, climate is not that predictable anymore. But thumb rules like it will continue raining here. We have and we will keep on having water to manage, also on mine sites, obviously. Average annual runoff rates correspond to that from 200 to 400 millimeters of water. Obviously that depends on the site location in Finland, also really local conditions, depends on the surface area, what we are talking about, and this is just a thumb rule. But kind of, even with the changing climate and in the future, we will keep on having surplus of water here on our mine sites, on our mine waste areas. So we will keep on having water to manage. And then now continuing to that part. So when we have mine waste areas and water, so what kind of things we have to understand there? So that we can do the water management and also the water balance models properly. So yes, site characteristics, as just said, climate, hydrology. Where are we? What kind of climate we have there locally? But then extractive waste, that's also to understand, like what kind of waste we have on the whatever we are depositing. Is it rock-like? Is it tailings? On tailings we have several kind of applications. We can have sludge-like deposition, and then we can thicken it a bit more, or we can have paste-like. It's even if it's thickened even further, so we can have a paste-like material, or even dry stacks will be introduced to Finland in a short while. Then those barriers or structures below around, and then also eventually on top, kind of understanding that what kind of structures on and surrounded by the extractive waste that we deposit will be structured on. And then the footprint, that's kind of because we have this from 200 to 400 millimeters of water to manage like annually on the footprint. So total area impacted, that's obviously kind of for water management. So that's important to understand. But then the deposition stages and kind of if there is, because often there is progressive construction of areas. So understanding that on which dates we are going to which area and how are the areas expanded over time. I start with this simple one. I have this kind of two graphs just presenting not everything. I will talk a little bit like to add to these figures. But so the first one is easier one if we have a waste rock stack. So we know the footprint. This one is kind of a, we may have it like kind of in a this kind of hill, but it can also be quite smooth, the area. But kind of we have to understand the footprint that we are from which we are collecting the water. And the precipitation, yes, that falls to the waste rock. In winter, we have it as snow. There is evaporation from the rock. So with hydrological models, it has to be kind of evaluated, or then also temp rules can be used, but how much then the water is evaporated from the rock surface and on which times of seasonal periods. But for the water that is not evaporated from the rock surface, so it then infiltrates to the rock material. It can catch elements from the rock and depending what we have on the basal structure, what we have on the bottom, so it either kind of then continues if there is a such system that kind of diverts the water to this kind of there is quite often ditches like around these waste rock areas. So there is like on top of the basal liner or basal system, so there is flow to these seepage water collection arrangements. But then there has to be also evaluated that what's the amount of uncaptured seepage. It depends on the engineered system on the bottom, but also the leakages have to be accounted for. And so there is a lot of kind of hydrological, but also like engineering related matters to understand before we get kind of to the amount of the pumped flow. For which, and this is the matter kind of that we need then for the water balance modeling. But the water balance of this area is formed by kind of understanding the system, understanding the climate where we are, understanding the processes and assessing the processes, how water flows from one area to another, and combining it all. And then it's a balance model, it's pluses and minuses, and then we get the amount of water that we have there to manage. And then the this kind of more complex waste rock is, well, that's rock. But then tailings, that's kind of tailing systems are always much more complex than what are those waste rock systems. So we can have a slurry deposition asset, and this example is actually if we would have a slurry or possibly thickened material, but then this kind of application might be applied. But slurry is something that is like, well, not thickened at all, or then just kind of slightly thickened. But on such materials, we are talking about tailings. So tailing sand is really fine sand if someone doesn't kind of is not familiar with that, but so we have solids content of, let's say, from 10 to 30, even 40% by weight. So that kind of solids content we have on slurry. Then by thickening, we can get it like from up to 60, let's say. Then if thickening even more, so if the material is such that paste can be formed, so paste on that we have solids content on the material, let's say up to 70-75%. And then with filtration, the material can be dewatered even further, and then we are talking about kind of cake-like stuff, which is not, it has moisture, but it's not like behaving, it cannot be pumped anymore. It has to be conveyed and stuck otherwise. But what's kind of concerning the tailings facilities and tailings area water management? Yes, there we also have precipitation. We have this kind of pool and wet beach area quite often, but then there is of course evaporation also from this area. But really important and kind of because we have quite often really wide areas and there is a lot of tailings material from the concentration plants. So what's this amount of water retained in tailings? So what's actually the tailings solid content on the stack when it's consolidated, when it's on the stack on intermediate state, but then also in long-term state. So for example, this is once again kind of a thumb rules, but if we deposit like slurry-like material, let's say from 30 to 40% solids content, depending on the structures, on the kind of draining structures of the system and how the surrounding of the tailing stack, basal dams, everything is engineered and what kind of systems there are. But quite often the solids content on the stack after on deposition, so that's like from 70 to 80% solids content. So there is still quite significant amount of water in the stack eventually in really long time. So then concerning this like water balance of the, which is kind of then quite often my part to understand. So those consolidation properties and settling properties are important to, really important to analyze for the material that will be deposited. But yeah, tailings areas are much more complex, but in any case, the kind of, there is similarities. So we do get the rainfall, there is evaporation, we have to understand all the processes that happen there. If there is water contained, that has to be understood. If there is seepage through systems, if the structures are engineered on such way that there is seepage through, and then it's collected, so those amounts. If there is uncaptured seepage, so that's as well, because we're talking about wide areas, so that's as well a component to really carefully look at and understand that what happens, how much water is going to which direction. And from all these, understanding all the processes, all the directions to which water flows, then we get the overall balance of the system. We have like, let's say from 5 to 10 minutes time here. So I will just shortly go to these water balances. So water balance, as we just saw and I said, but kind of water balance, it's the balance of the whole system. For each area or each component in a mine, we do have several extractive waste management areas. We have those water lagoons, basins. We do have other storage areas. We do have quarries, we do have a mine, like pits, we do have underground mines. So for each area, we need to kind of calculate the balance separately and form it, understand the processes which take water, which leave water. So what goes in, it either goes out or then it's stored. So that's kind of the basics of a balance. And so in Finland, because we do have this climate where we are, so this is the net positive stuff is that we do have surplus of water, which means that we need to either discharge water or then it will be kind of stored to the mining area, which kind of in a long run is not a situation that is wished. And this one I skip, but I will still present this one because not now focusing on the extracted waste areas only, but giving an insight of the mine site overall water balance. So kind of we always start from the concept and understanding the inputs, but then there is the modeling and then there is the results. But now a little bit like still focusing on the inputs. So areas, structural data, extractive waste areas, that's really one of the core things to understand that we get the mine site water balance kind of operating. We get the inputs to the modeling, climate asset, but there is also process-related data. We need the production data, water recycling kind of requirements and rules that are used. There is a lot of hydrogeological data as well. And then there is a lot of geochemical data that has to be assessed and understood so that we kind of get the whole mine site water balance model to function. We have the model kind of correct enough so that it can kind of give results that can be relied on and used on the analysis, both for the engineering, but then also for the environmental assessments. I think that I'm quite done here. If I want you to remember something from this, what I said, so remember surplus of water from 200 to 400 millimeters of water annually to manage, no matter which extractive waste area or area is there at hand. So thank you.